Hello, everyone. Welcome back. Third session of QWorld. Hopefully, everyone is enjoying themselves. Definitely lots of talks and lots of cool stuff. The stuff that I don't know about from the physics perspective. So yeah, today we finally get back down to writing code, seeing how to run simulations on stuff that we've been talking about just with the math. So I guess it's nice to just start with a brief perspective on things before heading deep down into this. And so the idea is, even though in our first talk, we motivated quantum computing from a classical computer science perspective as the killer app coming from Shor's algorithm, it's nice to always remember, right, that the initial proposal for quantum computing, one of them being from Richard Feynman, really came from this notion of simulating quantum systems. And that remains one of the key killer apps for quantum computing as well. And while there's an interesting debate surrounding whether or not we get to achieving scalable quantum computing with error correction and all that stuff, there's still interesting stuff to be had with NISQ quantum devices and what have you. So there's lots of interesting debates around that. And for people who might be interested in the bigger picture, if you're not familiar, there's a nice discussion and perspective from Jill Kelly on his blog. He's given a bunch of talks as well in terms of what would be required to give quantum advantage. So you could follow that. Right. So now, so what's the issue? We finished yesterday with this notion that if given quantum state has a tensor product decomposition, it would be simple to simulate classically. Hence, any interesting quantum system that's potentially not going to be simulable efficiently or quantum mechanically needs to have interesting correlations in it. And the problem becomes is that if you start doing a classical simulation of it, as soon as you start increasing your number of qubits, the amount of memory required for the classical simulation kind of blows up exponentially. So while the programs that we will be looking at using IBM Qiskit are a good way to start playing around with and simulating small quantum systems on your laptops, on your devices, really, you really want to be able to have access to actual quantum devices to really appreciate the benefit of quantum devices. So what does an actual quantum program look like in Qiskit, right? So Qiskit is one of the libraries among many libraries available today that allow you to play around with the quantum formalism that we've been working with. Recall that the quantum formalism that we've introduced so far is kind of error-free, noise-free, and relatively simple, doesn't have complex coefficients for its amplitudes. We assume they're real. Qiskit naturally allows for that general stuff, but we will restrict our kind of formulation towards that smaller kind of restricted perspective, right? So the file that I'm looking at right now on the screen is the one that opens up if you go to your Start notebook and open up this first quantum program with Qiskit. I'm assuming people have already gone through their setup of running Qiskit, ensuring that it's set up. If you haven't, work along with what's on the screen, and hopefully you can get it up and running later. So there's lots of text in this explanation, which you're welcome to read through. What I'll try to give you is brief crash notes on what the code is doing. So if you're already familiar with Python programs or some form of programming, what's happening in the first line is you're essentially including the kind of libraries that you would be using. Here, we are essentially importing from Qiskit the key libraries that we'll be using for our small program that we're writing. As one might assume, we'll need some quantum memory, we'll need some classical memory, and then we'll have a circuit representation of the computation that we do, right? So the standard formulation, just like in classical computation, is to think about your computation in terms of a digital circuit. We can imagine a very similar circuit formalism for quantum information and quantum computing as well. Now it's kind of a hybrid circuit where rather than just having classical bits, I also have quantum bits. And those are going to be essentially represented by getting information available and getting methods available from the quantum register and the classical register for quantum and classical memory, respectively. Both of them then will be combined into building a quantum circuit, right? So we first define our quantum memory over here by saying, all right, give me quantum memory. And I'm only really just asking over here for a single qubit. And I define an optional label for it, hey, that this is labeled as my quantum register QReg. Similarly, there's a classical memory that I define with just a single classical bit, and I label it as CReg. These two are then combined together in terms of building a quantum circuit, with us giving the two arguments. Hey, here's the quantum memory or the quantum register that I've prepared for the circuit, and here's the classical register I've prepared for the circuit. We can do an operation on the circuit, in the circuit that we are constructing, and the formalism then is the QC is the quantum circuit that we've just prepared. Within that quantum circuit, I want to apply the X gates on the single quantum bit that I have. The indices are labeled start from 0. So that's how it works out. So this would just mean that the single qubit that I have, apply an X gate on it. And afterwards, the computation is just measure that single qubit and store the result of that measurement in the classical bit that we had. And that's the reason why pretty much any quantum circuit that we prepare this way would always have a corresponding classical bit, so that the quantum bits that we've measured, the result of those measurements is stored in some classical memory, right? And then this finishes off our preparation of the quantum circuit. So we just prepare printing of a message that, hey, the preparation of the circuit is done, right? You can run this off, and the following kind of line comes through. So everything went well. All right, visualization of the quantum circuit. Just a simple, recall QC was the quantum circuit variable that we had defined, and then it has a simple method called draw, and we get kind of an ASCII art looking visualization of the quantum circuit. Let's kind of quickly look through. QReg was a quantum register. We only have a single bit of memory, so the label is just QReg 0, single classical bit of memory. Note both of them are initialized to kind of the 0 value. So we've got the ket 0 representing the initial value or the initialized value of the quantum bit, and the classical bit is also initialized to value 0. We applied a single X gate on the quantum bit. So that's what this is representing. And here then it's this measurement that we did over here on the quantum bit. And the two lines in the circuit, as is the norm in quantum information, represent, so the single line represents evolution, going from left to right, represents evolution of quantum information or the quantum states, and two parallel kind of horizontal lines or parallel lines represents evolution of classical bit. So the idea over here with this measurement M is that we measured the quantum states that resulted in some classical value. Recall how we in our formulation had been talking about set of states, and that those set of states have some labels. So the idea over here is that this measurement resulted in one of those labels with certain probability, depending on whatever the circuit was. And that label then is going to be thought of as classical value, right? It's a classical bit, let's say, for our purpose. That classical bit then is being stored into this classical register. That's what this visualization represents, right? Yeah, what we're identifying is, rather than doing this ASCII art kind of visualization, let's use matplotlib, one additional library for doing this visualization. So we get a nicer looking visualization, which still represents exactly the same circuit. So nothing has changed in a circuit logically. All that has changed is that we've got a nicer looking visualization of exactly the same circuit. So previously we had just qc.draw, we get this picture. If you say, hey, use this library, matplotlib, then we get this visualization where this represents the measurement. The result of the measurement is again being stored in this classical bit. All right, so relatively straightforward. Questions about stuff so far? What would be the value that we get in our classical register? Initially, we had prepared quantum state in state 0. We applied an X gate on it. We've already seen the formulation of an X gate. It's a flip gate. It's also there in classical information and classical computing. We do a measurement. So what would be the value of the classical register after this? Great, 1. And so we expect that the measurement result will be a 1. Naturally, so far, we actually haven't executed the circuit. We actually need to do the computation corresponding to the circuit. And so what we have done in the first part is building a circuit. We have visualized it as well. And now the second component of working with Qiskit might be viewed as executing the circuit. For nearly all of the computations that we're going to be doing in QBronze, we are going to be executing these computations locally, i.e., the computation is going to be done on your devices. You're not going to be necessarily computing anything on the actual quantum devices that IBM makes available over IBM Cloud, even though it's possible to do so. Just that within QBronze, we won't have an occasion to necessarily use it. So for the execution part, yeah, kind of the standard commands. There's much more to say about it. We'll restrict our attention to simple stuff for the moment. We need additional stuff imported from Qiskit for the purpose of actually executing the circuit that we've built. We need agreed. In this case, we will always get output 1, and we'll verify this soon. So we've built the circuit. Now we want some backend library from Qiskit that allows us to actually execute it. There are different execution libraries available. We'll be using something known as the QASM simulator, QASM, quantum open assembler, if I recall that as open quantum assembly language. So that's the simulator that we're using. So this line can be read as that I've prepared a job to be executed. That job corresponds to us having to evaluate this quantum circuit. The kind of backend evaluator, kind of the simulator that I want to use in terms of how I want this quantum circuit to be evaluated, corresponds to this custom simulator. There are other options available. We'll have occasion to look at some of them later. What would be the key difference? Right now, the only thing that we'll get from our computation are the output statistics from the running of the computation. There may be cases where I'm actually interested in, well, what's the actual quantum state at the end of a computation? What was the actual unitary that corresponds to the circuit that we've built? So there are other backends available via Qiskit that allow us to do so. For the current purpose, we are essentially just saying, hey, use the simulator. This will allow us to run our circuit and just get the statistics out. Naturally, because we want to generate some statistics, we've got to tell it how many times should it evaluate the circuit. And so this parameter over here is telling it, hey, run this circuit order of 1,000 times. You can change it as you like. For our current purpose, this is the value we're fixing. So for the purpose, let's assume everything is noise-free. There are formulations that will allow you to design open quantum systems and work with that formulation as well. Since we haven't done that so far, we won't touch upon it. The output from this computation then are the statistics. How do I get those? The job that was just executed, the results give us a parameter get counts from the quantum circuit that was executed, counts store that result, and then I can display those statistics via print counts, right? And as we expected then we are visualizing this as an histogram. And over here, there's also this text display of the print. Note we executed this 1,024 times, and the output is saying all of those 1,024 times, the output label came from the measurement in the classical register was 1, all right? So classical values naturally will be, the classical register is a classical bit. It will store only a 0 or a 1. In our current case, the statistics that we have obtained basically say that in all the 1,024 runs, we've got 1 as the output. Quick visualization as a histogram gives us exactly that. You got the output 1 with probability 1. All right. So in this case, it is a power of 2, right? So 1,024. But I don't recall what it has, unless there are some details I'm missing about Qiskit, why it necessarily needs to be a power of 2. Maybe there's something I'm missing. All right, some details about the quantum assembly language simulator that we essentially just used. And stepping back from it first, well, if you think about running programs on a classical computer, don't worry about quantum computing. Naturally, we already understand that there's this interpretation that's happening where you take a program, let's say written in Python, C++, pick your favorite programming language, and then there's a conversion process of that program getting converted into some low-level language, and then maybe directly getting converted into the assembler for assembly language for the hardware that you're running or compiling that program in, and then that assembly language being executed at machine level on the processor that you are running your code on. As classical computer scientists, some of the times you look at these, some of the early tradition pioneering results, which are labeled by Hayes and so from this great result regarding how programs should be compiled and computed, and you realize, hey, wait a minute, I could have come up with that. And if you've ever been in that position, it's great to know that you kind of find yourself also in a similar position now, where just like 60, 70 years ago, people were figuring out, hey, what's the right way to, well, even though people are still figuring it out, how to design processors, what's the right architecture. Similarly, the field is kind of wide open in terms of what's the right architecture for a quantum processor, naturally. That's at the physical hardware level. But then there's also kind of this hybrid question about once I've written this high-level program, and even though the one that we're running is still a simulation, you can just imagine now saying, hey, what I want to do is to run this program on an actual quantum processor. What's a good way to transform the high-level code that I've written into low-level machine code for a quantum processor? And there are lots of interesting open questions out there on this issue that require both a good grasp of classical computer science kind of tools as well as the physics of it. And so for people who are interested in open questions in this area, training yourself in both these kind of skill sets will be really useful. It is possible to see what was the output of the quantum assembly language, the simulator that we just used. So you take that circuit and you just call QASM method on it and print out the result. And what's happening then is that the corresponding quantum assembly level code gets printed out, and it's kind of self-explanatory. You have one memory of a quantum register, one memory of a classical register, and then you apply the X gate on the quantum register, and you said measure the quantum register and store the value in the classical register. Perhaps it's kind of even simpler than the high-level code. But you could imagine now how this might become more interesting and complicated, where you're not applying just an X gate, you're applying some more interesting, complicated gates. how to decompose that gate into some traditional set of gates, right? So just like when you write a program on a standard classical computer, it at the end of the day is going to get compiled into just the basic machine instruction sets that are available on your processor. Similarly, these quantum instructions do need to get compiled down into the basic instruction sets available for the quantum processor. And how that conversion process should work, what exactly is an efficient instruction set for the quantum processor to make available, are really interesting, cool questions to investigate, right? But we won't have occasion to talk about that for now. Quick generalization of the same circuit. So you've got a couple more qubits now. So you take 4 qubits, you've got 4 classical bits. Again, prepare the quantum circuit for it. What are we doing over here? We're applying the X gate. We are applying 2 X gates on the top level qubit. We are applying 1 X gate on the last qubit, 3 X gates on the third qubit, and 4 X gates on the second qubit, right? So if you work out the indexing and do the visualization, then this is the quantum register that works out. So this is just kind of a small exercise again to make sure we understood what's happening. This little dotted line over here is just the result of QC2 dot barrier, which is just there to improve your visualization for a complicated looking circuit, where you're kind of doing just a logical partitioning of saying, hey, let's introduce a logical barrier between what's before and after, not really changing the computation that the circuit does. Note that the first quantum bit that we have shows up on the top, and then the first, then the second, and the third. You can flip this order as well using this input argument, and note the difference between these two visualizations then is over here you've got QREG 0 at the top, whereas over here you've got QREG 3 at the top, right? So just the order of the qubits got reversed, depending on whatever kind of formulation or standard notation you want to work with. Note here that you still see just one C reg, right? But you've got this kind of bar over here showing that there are 4 bits over here. And this is showing which classical bit is the measurement result then getting stored in. Why would you reverse the order? Sometimes for purpose of computation, sometimes also just in terms of standard formulation, in terms of when you draw the circuit, which way do you want to index the labels of which qubit you're representing. So it can end up being just a matter of preference as well. It's not necessarily changing anything necessarily for the purpose of computation. It's just which way do you want to index the qubits in your representation and the visualization. What would be the output? 2 x's will negate themselves. So even number of x's will negate themselves. Odd number of x's will not negate themselves. That's kind of the same thing as flipping it. You've got 0, 0, 1, 1 or 1, 1, 0, 0, depending on whether you reverse the flip bits or not. So if you took the case where we had reversed these orders, where we are applying the odd number of X gates on the first 2 top over here, and even number of X gates at the bottom 2 over here. So the output comes again 1, 1, 0, 0 for all the 100 times that I run this simulation, right? So Constantine, hopefully it's clear why there's a difference from 0, 0, 1, 1 rather than 1, 1, 0, 0, just because we reverse the order of the qubits. Right? So then you've got a nice little exercise over here to work through, which we'll leave for you to work through. And we'll move on to one little additional exercise that we'll work through during the session today. So how about, so I've got this visualization of circuit already done over here from early on. That's not actually already part of your notebooks. We'll build this circuit right now. This has a new gate, 3-qubit gate that you may not have seen before, which is just a generalization of the C0 gate. Well, the visualization of a C0 gate might be, you just have this one filled in dot with kind of a plus sign on the second qubit, which have been a C0, with the first qubit over here as the control qubit and the second qubit over here be the target qubit. This then is the Toffoli gate, which is also called the control not gate, where you're treating, in this case, the first and the second qubit over here as control qubits, the third qubit over here as the target qubit. And the idea is very much exactly the same as the control not gate. If both the first and the second qubits in this case are set to 1, that is, both the control qubits are set to 1, then the target qubit is flipped. So now, very quickly, if everyone has been following along, what would the matrix representation of a CC0 look like? You don't need to write down the entire 8x8 matrix, just try to figure out what the key idea would be. In the matrix representation of the CC0 gate, where I'm suggesting that it won't be 3x3, right? Recall CC0, the control not gate, which was a gate over 2 qubits, was already 4x4. So this is a gate over 3 qubits, so 2 to the power of 3, 8x8 matrix. but I don't want you to write down the entire 8 by 8 matrix over here, just the key idea in terms of what the 8 by 8 matrix representation would look like. It's a very sparse matrix with just some entries set to 1, only 8 entries set to 1, and even those in a very nice pattern. So recall, for a single qubit, the gates were 2 by 2. For 2 qubits, you just get 2 square times 2 square, so 4 by 4. 3 qubits, n qubits, 2 to the n, 2 to the n. So for 3 qubits, you then get 8 by 8. So 1, 2, 3, 4. I'm not sure how to read those because you're writing it as a 4 by 4 matrix, and this will be 8 by 8. But I think you've got, may still have the right idea. It's really exactly the idea from a C0 just generalized to the 8 by 8 matrix. So people who are still writing 8 by 8 completely agreed. Yes, it's an 8 by 8 matrix. The question is, what would be the difference, or what would be the actual entries of the 8 by 8 matrix? Block diagonal, mid block diagonal, and identity, no. Very cool, right? So identity, tensor X. Is that actually the case? Identity, tensor X? Right. So you want to verify whether identity, tensor X is the matrix representation of CC0 gate. Please do verify identity, tensor X, because that's then just the X gate on the third qubit, whereas this is something more interesting. Control on the value of the first 2 qubits, apply a NOT gate on the third qubit. Right, so it's much more interesting than just saying apply a NOT gate on the third qubit. And so someone, I think, already mentioned it, right? So the entire diagonal is identity except for the last 2 entries, but the last 2 entries are again kind of anti-diagonal. In fact, if you go back to the Qiskit reference, it has a nice representation of exactly the CC0 gate, and you note exactly then these 2 entries at the end are flipped to 1. And the idea again is what we had in C0, that these 2 columns correspond to the first 2 qubits now set to 1. And then for these 2 cases, in the output, we want to flip the value of the third qubit. And so that's why we get this anti-diagonal rather than the diagonal in this 2 by 2 block diagonal over here, right? So that's the CC0 gate, and it's really interesting and useful. We just have a simple circuit over here to work with the CC0 gate. CC0 is also the Toffoli gate. It's really interesting for the purpose of reversible computation, etc. as well. Again, we may talk about it a little bit more once at the start of QSilver, but for the moment, we just take it as a given. So hopefully everyone is now okay with what the CC0 gate is. If you're not, again, go back to this Qiskit reference that's available to you over here. And you've got both the matrix representation for it over here as well as the definition description of what it does, right? So flip the third qubit if the first 2 qubits are 1. Now, what I'd like for people to do, and ideally people who may not be actively contributing, new people to come in Discord, is help me write down the code for building this circuit, assuming the standard importing of the libraries has already been done. Now just write the code for building this circuit line by line. So maybe you want to open up the previous examples that we've already seen locally on your end, and then just shout out on Discord line by line. Don't just copy paste the entire code that you built locally, but perhaps line by line, individually, people might shout out, how do I build code that would correspond to this circuit that we've got on the screen. The only new thing over here is the CCX, for which I've already shown you how to write the code for it. So I'm looking ideally for people to give actual code. QC equals quantum circuit 3. I'll follow exactly the template from the previous code that we have seen so that people don't get lost in terms of the construction. Note that previously we started out first building the quantum registers. Let's build a quantum register. We've seen 2 examples called Q1, Q2. So we've got kind of Q3 as the third quantum memory. It will be quantum register. And in this quantum register, I'll need now 3 qubits. And I'll still give it just a label of QReg. Right. Analogously, I'll have classical memory. How many classical bits do I need? So there are some results some inputs over here that are mentioning 3, but note that in the circuit that I have, I only measure 1 qubit. So yeah, it suffices to actually just measure, since I'm measuring just 1 qubit, it suffices to have just 1 classical bit. So I can just say classical register 1 and give it the same label, QReg, and then combine these 2 in my quantum circuit. QC3 equals quantum circuit. I've got my quantum memory in Q3 and I've got my classical memory in C3, so that's done. Now on the first qubit, I want to apply a Hadamard. What's the code for that? It's essentially the same code as applying an X gate, except that X gets replaced by H. Excellent. QC3 dot H. What's the input over here? Which qubit am I applying this quantum gate on? Esra, keep tuned. We will talk about exactly this, a bit of this in QSilver. It's not necessarily that straightforward to take arbitrary classical circuits, quantum version of it. There's an additional bit of issue that we need to keep track of, i.e. reversibility. Classical circuits in general are not reversible. Right, so we want to apply Hadamard on the first qubit, which in this case will be indexed by 0 on Q3, so Q3, 0, right? Then I don't move right away apply Hadamard again on on Q3, 0, because first I've got to apply now the CCX, the Toffoli gate. What does that look like? So naturally it will still be like QC3 dot something. What's that something? Right, CCX. What are the inputs or arguments? 2 reg 0, 1, 2. Yeah. So, all right, you've got the full answer. Right. So you just give the order. The 2 control qubits will be index 0, index 1. So you just give them here Q3, 0, Q3, 1. And then the target qubit is Q3, 2. Right. Unless I made a typo, that should be correct. Then I again apply the Hadamard on the first qubit. So that should be the same code. Now I want to do a measurement and store the result in my task in memory. What does that look like? Sorry, I'm not labeling my code with comments and stuff, but everyone is on the spot in terms of figuring out the code correctly. So comments not needed. QC.measure, Q3, and store it in C3, but Q3, 0, right? Not so, just to be precise. So I have my quantum circuit. I want to perform a measurement on it. Which qubit am I measuring? I'm measuring Q3, first qubit, and I want to store it in C3. Should this give me the circuit that we have below? What's the line for visualization? Well, we can literally copy paste exactly the code that we had previously. So good, excellent. We get exactly that same visualization. Excellent. Before we move on to actually executing the code, what's the measurement result, expected measurement result? Right, so people are saying 0. Why? 2H gates. But there's the CCX in the middle. I'm measuring the first qubit, right? And no phase kickback, okay. Cool. So people are definitely ahead, right? So there's no phase kickback, etc., to take care of, whatever that is. So yeah, we will get, or we expect the output to 0. Well, we take again, copy paste exactly the code. We have a circuit QC3, perform the simulator on it. Let's just run it 100 times, print the counts, and yes, indeed we get 0 exactly 100 times. Now, here's my question to you: could there exist a possibility in which the measurement result on the first qubit, i.e., the qubit that we've just measured, comes out 1 with certainty, assuming I don't change anything that I'm doing on the first qubit? The circuit remains as is, but I'm allowed to perhaps change what the quantum states are as input for the second and the third qubits. The first qubit also remains as is, the circuit remains as is, and the only thing I'm allowing you to do is to change the second and third qubits. The reason why I'm kind of being very explicit about this, because so yeah, people are saying no. So if the circuits remains as is, and the only thing I'm allowing you to change is the second and the third qubits can potentially change in terms of what states they are. The reasoning that we use for figuring out why the first qubit is 0 seems not to be affected, right? We said, hey, CCX doesn't really affect the first qubit. It's just being treated as control, and the Hadamards will cancel each other out. So the first qubit won't change. And that indeed is completely perfect, classically valid reasoning about such a circuit. But let's try to verify whether that actually is indeed the case in quantum circuit as well. So let's take a break from the circuit and move back to our slides. Just give me a second for setting those up. Right, so people agree that that's essentially the circuit that we had, except that now I'm explicitly labeling the second qubit and the third qubit as general qubits with parameters alpha, beta, gamma, delta for their amplitudes. The first qubit is still in the state 0. Agree? And so what we'll do now is a quick exercise in working through evolution of a quantum circuit by hand. I know we've got a circuit evaluator with us. We now have kind of an arbitrary computation in terms of parameters alpha, beta, gamma, delta, right? So let's try to work through it, and it will also give us practice in understanding evolution of quantum circuits in general for people who may not have seen this before. Everyone on the same page? So first agreement that I want to get with is for people to verify that the circuit that I have now on the screen, it's the same circuit as the one we had in the simulator in Qiskit, except that the second and the third qubits are now written in general states. Okay, what we'll do is try to write down kind of what the states or the joint state representation is of the 3 qubits after each of these individual steps in the circuit. And so let's call this T0 T1, T2, T3. First step is relatively straightforward. The initial joint state is 0, tensor alpha 0 plus beta 1, tensor gamma 0 plus delta 1. Right? Yeah, the only difference is that the states that I've initialized for qubit 2 and qubit 3 are arbitrary qubits, where alpha, beta, and gamma, delta are the general parameters for a qubit. So that's the state at time t0. Let's evolve it to time t1. The only thing that's changing is I've got Hadamard applied to the first qubit. So i.e. I'm saying Hadamard tensor identity gives me the first qubit evolved to the plus state, right? So it will be 1 over square root 2, 0 plus 1 for the first qubit. Tensor still kind of, please bear with me, 0 beta 1, tensor gamma 0 plus delta 1. Agreed. Actually, in order to help us in applying the Toffoli, rather than applying the Toffoli in this representation, let's kind of take the tensor product in this get notation and write out the states such that we group together the first and 2 qubit states together. So it helps us to identify when to apply the Toffoli gate. What would that look like? So we are essentially just saying, hey, combine these 2 qubits together in the representation that we have. So we write down, so we're not going to T2, we are just rewriting T1. We'll still have 1 over square root 2, alpha 0, 0, plus beta 0, 1, plus the third ket in this representation would be alpha 1, 0. Excellent. And I'll stop here in terms of the grouping, right? Because these are the 3 cases for the first 2 qubits for which the CCX will not result in a flip on the third qubit. And then this is tensored with gamma 0. And I've just dropped explicitly writing the tensor product sign. Hopefully that's okay. Right, so that's that. Plus the fourth case where I still have 1 over square root 2. Now beta 1, 1, again tensored with gamma 0 plus delta 1. Agreed? Now we move on to step T2. We apply the CC0 or Toffoli, and the state would evolve to, the only thing that now changes naturally is something will happen over here. Let's kind of quickly write out. The first part naturally remains as is, 1 over square root 2, alpha 0, 0 plus beta 0, 1 plus alpha 1, 0, gamma 0 plus delta 1. Nothing changes in the third qubit because the 2 control qubits were not 1, 1, plus beta 1, 1 square root 2. And now what would be now the state of the third qubit in this case? Only gamma 1 plus delta 0. Thank you. Gamma 1 plus delta 0. And you want to compare that. That's essentially just the application of an X gate on the third qubit. Now comes the bane of everyone who does start evaluating quantum circuits for the first time is, let's do this major expansion of this quantum circuit, quantum state, because we are applying Hadamard again to get to state T3, i.e., which will mean each of these individual first qubits will now be expanded out into their plus minus state. And so you get a really long, messy expression. How about we give 2 minutes for everyone to work out what this entire expression would simplify out to, i.e., what's the result of now computing H tensor I. It's not nice looking to begin with, right? It will be reasonably long. Why? Because the first state is again getting expanded out, and it's by application of Hadamard, and there's no nice, simple, necessary cancellation that's happening that's obvious. So you'll have to explicitly do the calculation. So I'll give everyone a couple of minutes to work it out, and then I'll write down what I have. Why did we split again the terms that way in the first H gate? Because it made us easy to apply the Toffoli, because the Toffoli is applied by basically saying when the 2 control qubits are 1, 1, then flip the third qubit, i.e. apply an X gate on the third qubit. The way we kind of decompose this basically said, hey, in these 3 cases, the first 2 qubits are not 1, 1, and so nothing will happen to the third qubit. And in this case, the 2 control qubits are 1. So when we apply the Toffoli over here, note that the third qubit actually got flipped. Right, we exactly isolated the 1, 1 in the first 2 qubits. Double control means that if either of the, both need to be 1. So that's exactly what we are doing in the computation over here, right? Exactly when both the controls are 1, then flip the third qubit. So people are giving me stuff written in the plus states. So for the purpose of our computation later on, it will help if we have the kets in kind of the standard basis. So just the 0, 0, 0, 1 stuff. I know it's tedious. Let's kind of try to expand it out. So the first thing we have over here, let's actually do it this way. So I've got alpha 0, 0. Oops. Over here, when you apply Hadamard on the first qubit, the 0 expands out into the plus state, 0 plus 1. So let's write it that way. So you've got half alpha 0, 0 plus alpha 1, 0, right? Don't put the bracket. So that's the expansion from the first qubit, or this yellow highlighted stuff. And then you apply Hadamard on the beta 0, 1 part. That expands out into beta 0, 1 plus beta 1, 1, right? Then you've got the alpha 1, 0 part. Yes, these two qubits that I'm writing separately do correspond to the first two qubits, which are the control qubits, right? Then we perform it on alpha 1, 0. So that expands out into, now the first qubit is 1. So the expansion gives us the minus state. So we have a minus sign to keep track of alpha 0, 0 minus alpha 1, 0, right? So that's the expansion of Hadamard. And then the third qubit naturally remains as is. You just got gamma 0 plus delta 1. Why minus? Because in this case, when you apply the Hadamard was applied on the first qubit being on the one in the 1 state. Hadamard applied on 1 gives us 0 minus 1, hence the minus sign. Finally, we apply it on beta 1, 1, and so that gives us plus beta 0, 1 minus beta 1, 1, right? And the fourth qubit remains as is, third qubit, sorry. And so that will be gamma 1 plus delta 0. All right. So tedious, but fine. You simplify this out by collecting the terms together, and I get something that looks like this. Half, let me just copy it out, 2 alpha gamma 0, 0, 0 plus 2 alpha delta 0, 0, 1 plus beta times gamma plus delta 0, 1, 0 plus beta times gamma plus delta 0, 1, 1 plus beta times gamma minus delta 1, 1, 0 plus beta times delta minus gamma 1, 1, 1, right? So unless I missed something or made a typo, this should be fine. Verify that. Do we have all the 8 terms? No, right? So that's kind of interesting. So the computation isn't necessarily giving us the superposition or all 8 possibilities that might occur. Right, and that might be understandable because the first qubit we've still restricted to be initialized in the 0 state. We've got 6 of the 8 possibilities. So I'll copy this again on the next slide. Oops, it doesn't want to move to the next slide. Oh, well, let's write it over here for the moment. Thought I could decrease its size. I'll keep it at the bottom over here for now for reference. All right, so that was the state that we end up with. Now I ask, let me ask a bunch of questions. Probability for first qubit to be in state 1. This is just application of the Born rule that we looked at last time. So based on this joint representation of the quantum state, this is the state that we have in general just before the measurement. What's going to be the probability of getting the first qubit in state 1? We right now can't get a full 0.5% because of these alpha, betas, gammas running around. So what would we need to do? Essentially, what we're just asking is, well, first, let's just look. What are there kets in here with the first qubit set to 1? And indeed, there are. There is this one, there's this one, and those are the only 2 ones. But that's interesting, right? There are 2 interesting kind of expressions here where stuff has first qubit set to 1, and it's not obvious that it will be 0 or whatever it will take, right? So based on this, apply the Born rule, and you take the highlighted kind of amplitudes, and you get this probability to be, as pointed out, half times. And we're assuming real parameters here, so let's not worry about magnitude signs and stuff. Gamma minus delta squared, right? Or delta minus gamma minus delta, same thing. Right. So let me ask one more question before we move to our original question. Sorry. Given that first qubit is in state 1, what is the probability distribution for second qubit? I.e., even though the circuit doesn't show a measurement on the second qubit, right? Great, Lolita, as we can directly see in the circuit, in the 2 cases, so you can kind of just do away with this entire vector part of the vector, right? Because we don't have, in this case, the first qubit set to 1. We are conditioning on the measurement result of the first qubit set to 1. So we just look at the second qubit. The second qubit in both the cases over here is in state 1. Hence, the second qubit now can never be found in state 0, assuming the first qubit was measured in state 1. So if the first qubit is measured in state 1, and we don't know what's the what are the chances of that going to look like here, what kind of generic expression for that, but it's interesting enough. If we started out with an arbitrary superposition of the second qubit, conditioning on the first qubit's measurement result to be 1, then we can say that the second qubit is always 1. All right. Oh, all right. Let's just give it a cat. All right. Finally, our question. I think someone already gave the answer when I asked it earlier, but it's nice to work through the solve. Does there exist a choice of alpha, beta, gamma, and delta for which first qubit is measured in state 1 with probability 1? So going back to the previous question, recall how did we obtain this probability? This probability was obtained by noting that the only two, so what does this entire kind of state representation show? This is the representation of the 3 qubits just before the measurement. Then in the first part, we said, all right, let's perform this measurement and figure out what's the general expression for the probability of the first qubit to be found in state 1. Well, you just kind of do a loop over these kets and say, well, what are the cases in which the first qubit is in state 1? And these two highlighted cases are the only cases where the first qubit is in state 1. We figured out a probability based on that, which gave us this. Then the second question asks, conditioning that this has already happened, that the first qubit measurement result did give us 1, what's the probability distribution for this a measurement on the second qubit? And here we just trivially note that in both the cases, the two kets where the first qubit was 1, the second qubit is always 1. And hence, the second qubit would always be found in the state 1, condition that the first qubit was found on the state 1, right? And then finally, we're asking, is there a choice of alpha, beta, gamma, delta such that the first qubit is always found in the state 1? And as some people are already kind of working through, one choice that works is you just say alpha equals 0, beta equals 1, gamma equals 1 over square root 2, and delta equals minus 1 over square root 2. You fix these choices, and you can verify that by basically just plugging it into this expression. Delta is minus 1, gamma is minus 1 over square root 2. So the 1 over square root 2's add over, got a square, so you get a half effect over there. So 2 over square root 2, and then, so let's actually work it out. Right? So why does this give you this? Half. Beta is 1, so that's 1 square. Gamma is 1 over square root 2 minus delta, which will give you 1 over square root 2 whole square. And so that you can verify will give you what? So this entire expression simplifies to, thank you. That's your probability 1. All right, so time to step back and marvel at what we just learned. Our initial classical kind of evaluation of this circuit doesn't work. So and this is a mistake I made the very first time I saw this circuit as well. Oh, wait a minute, I just, it's a CCX in the middle, the two Hadamard's cancel. Obviously, the first qubit would always remain in the state 0. And here's the kind of the nice effects of amplitude cancellations but why we need classical, so the classical register in the Qiskit representation is just to store the result of this measurement that we're performing over here, right? In this mathematical representation and computation that we're doing on the slide, we're just storing the result of the measurement, I guess, in our minds. But when we're doing this computation in a simulation, in a program, then obviously you need to store the measurement result somewhere, and that's why you're using that classical register. So what has happened over here is a nice kind of our exposure to amplitude interference. You're already familiar with it, perhaps from a physics background, in terms of interference patterns that you start out with in stuff like double slit experiment. We already saw, again, the effect of these amplitude cancellations when we compared classical coin flip versus a quantum coin flip. And here, kind of, it's again a nice example in terms of an actual computation, in terms of how stuff is happening. If you recall, in multiple different speakers have emphasized that in quantum computation, what you're essentially doing is, as someone likes to call it, you're playing a grand symphony where you want these amplitudes to cancel out in such a way that this crescendo or amplitude amplification happens for the right answers and destructively interfere for the wrong answers. Naturally, here there's, for our toy example, there is no such thing as a right and wrong answer, but we still saw how our kind of classical logic of thinking about computation doesn't work through because of amplitude interference that happens, right? So stuff or events in the sample space that we expected would have probability 0 have non-zero probability. In fact, they can be forced to have probability 1 if you play around with the amplitudes just right. right? So it's a really nice kind of takeaway. Let's do a quick verification that indeed we kind of got everything right in our computation by now going back to our circuit that we built in Qiskit. I assume there are no questions about this computation that we just did. Let's do a quick verification. I'll share my screen again. That's my Zoom. And share screen. Let me make sure the screen has been updated. I don't. Yeah. Okay. So quick question going back to Qiskit programming. How do I now change this circuit such that I do the verification that we just did in our computation? So I want to verify that there exists a way to input qubits 2 and 3, or QReg 1 and QReg 2, such that the measurement result on QReg 0 gives me 1 with probability 1. Right? So people still going through the evaluation of the circuit. Fine. So the question is, obviously, I need to change something in this circuit construction right now, right? What do I need to change? Here, I have fixed QReg 1 and QReg 2 to be state 0. That's not what I want in the evaluation that we just did. In the evaluation, QReg 1 needs to be state 1 and QReg 2 needs to be state something based on the parameters that we just figured out. So based on the parameters that we just figured out, can you tell me how to modify the circuit? So maybe the indexing is slightly off, but here I got the right idea. So in our initial state preparation, in addition to the Hadamard, we need to apply these gates. And why are we doing these gates? Recall that in QReg 1, our requirement was beta equals 1. So that gives us state 1. That essentially means I just need to flip the qubit from 0 to 1. Whereas qubit 3 had parameters gamma equal to 1 over square root 2 and delta equal to minus 1 over square root 2. So that's not saying just apply Hadamard, but rather I need to apply Hadamard to state 1. So I first flip the qubit 0 to 1 by applying X gate, then apply Hadamard to get the minus state, and then everything should go through, assuming I didn't make a mistake. Let's verify. And now, good, we didn't make a mistake in our calculations. Now, rather than getting output 0 with all the time, we're always getting output 1 as a measurement result on the first qubit. All right. Questions, issues, concerns, queries, sarcastic remarks. I think that's kind of a nice kind of thing to think about in terms of how our intuition using classical computation and evaluation of classical circuits doesn't necessarily carry through. And we'll essentially this is the key trick that will end up happening in every quantum computation, quantum algorithm that's doing something interesting, that's allowing you to do something interesting, is that you're orchestrating the amplitudes to work out in the right way in terms of constructive interference and destructive interference, or in the quantum algorithm kind of terminology, amplitude amplification. Good, we still have time, so lecture is not done yet. So if you go back to your notebooks, now you've got a couple of other stuff to work through in terms of visualizing qubits on a unit sphere, thinking about the operations that we have in terms of thinking about this as rotations and reflections. And that's what I'll quickly talk about, unless there are, I think, some technical questions related to the query, to the computation that we just did, which is fine. People can kind of figure that out on Discord while I'll move through to a couple of additional examples back to our slides. So let me share again, go back to our slides. That's what we've already done. Good kind of summary to talk about what is in the remaining notebooks for today. Make sure I'm on the right slide. Right, so given that we are working in this restricted model of qubit with real amplitudes, I already mentioned that it's possible to think about this as basically just a unit vector on unit circle. Note that within this visualization, you would then end up having you can have state 0 being represented on this x-axis as over here, whereas state 1 ends up happening over here. You've got state -0, state -1, and then a standard rotation matrix would end up being corresponding to applying a counterclockwise rotation, starting from state 0 to kind of whatever you want in terms of an angle theta, right? So if you had a rotation operator, the standard way you write it out, cosine theta minus sine theta, cosine theta. And then you've got stuff in the exercise notebooks that talks you through visualizing qubits in this way, thinking about rotations and reflections of operations on this unit circle, assuming that an arbitrary qubit psi is listed as we wrote last time as cosine theta 0 plus sine theta 1. Let's try to quickly summarize that discussion. there's a Z operator, which is represented as 1, 0, 0, minus 1. Quickly, let's figure out what would be the net effect of this operation on just the basis vectors. So if I apply the Z gate on the 0 qubit, what do I get out? This score is down, right? Z applied to the 0 qubit gives me, actually, so it's just 0 again. So Z applied to 0 is just 0. Although, as we'll discuss later on in much detail, 0 and minus 0 for the purpose of experiments are indistinguishable. But yeah, we just get the 0 state. But Z applied to 1 gives us minus 1. Excellent. So we introduce the sign flip over here. In terms of, and that's what the programming exercises will help you through. And so in this case, you can just literally multiply do matrix vector multiplication, i.e. 1, 0, 0, minus 1 applied to 1, 0. That gives you still 1, 0. And 1, 0, 0, minus 1 applied to 0, 1 gives you 0, minus 1. That's all that we've done. Right. Now, how would you think about this geometrically? What kind of operation is the Z matrix performing, or this operator performing on a unit circle, right? A unit circle. Flipping around the x-axis, rotation, what kind of rotation? So that's exactly kind of one of the nice exercises for people to work throughout. Is it a rotation, or is it rather a reflection? What kind of rotation, what kind of reflection? So pi rotation, no, so 0 stays at 0, where 1 goes to minus 1. So it can't be exactly that, right? There's something off in that. And this is not the bit flip, X is bit flip. But bit flip can again be thought about in terms of rotations and reflections again. So the programming exercises then lead you through thinking about what is the net effect of Z, what is the net effect of X in a geometric visualization. And why that's kind of nice and important as well is when we get to Grover's algorithm towards the end of our workshop next week, we'll see how a complicated looking algorithm can still be broken down just kind of on a two-dimensional plane in terms of just rotations and reflections. But in order for that to make work, you should spend a bit of time kind of thinking about what these matrices correspond to just within this two-dimensional unit circle, right? Okay. So I won't necessarily give away the answer right away. Some of the answers are in the programming exercises, some of them you build up via the programming stuff that you do. Reflection around X. So someone is talking about reflections rather than rotations, exactly for you to work out in the program exercise. So that's all fine. What I want to build up towards before the big grand protocols Monday session is talking about an introduction to quantum entanglement. So here's a circuit using gates that we've already seen. Assume that the starting 2 qubits are just in state 0. Then what does this circuit give us? So I really like the conversation happening regarding how to understand it as a reflection rather than rotation. Great. People should carry on with that after the session. But let's just finish off with a couple more slides on topic that we'll move into in our next session. So this is a standard little small circuit that helps us build something that is essentially, if you wanted to pick up one poster child example of what represents quantum information, it would be this. If you start out in the state 0, 0, apply Hadamard on the first qubit, the first qubit then becomes plus. So you've got over here the state as plus 0, still a tensor product decomposition, but then you say, hey, all right, apply C0 to this gate. So, well, let's expand this out. 1 over square root 2, 0 plus 1, tensor 0. Let's not write the bracket, just the 0 here. So that's still equal to just 1 over square root 2, 0, 0, plus 1, 0. Note, right? This way of writing it out makes it clear that the state is still kind of separable. But now once you apply C0, then we get, well, this, nothing will change over here. But over here, 1, 0 will end up becoming 1, 1. And so you get our Bell state, 1 over square root 2, 0, 0, plus 1, 1, right? And for people who seem not too familiar with ket notation, that's just this vector. And now I'd like to take a pause and connect this back to something that we did in our first session, where we had correlation vector for a 4-size probabilistic bit versus what you've just seen, which is, as is called in the literature, entanglement. Correlation we noted by this vector half 1, 0, 0, 1. Versus this entanglement, this Bell state vector being represented by this. Right, so the only difference for the moment in this representation between my perfect correlation classically versus a quantum entangled state, which is called also a Bell state. There are 4 of these as well that can create a basis for 2 qubits. What's the difference between these two, apart from the obvious kind of square root 2 versus 2 running around, right? And I wanted to kind of go through a little kind of thought experiment that I think nicely illustrates the difference. So lots of times in popular descriptions of quantum information and discussions about what's unique about quantum information, you'll hear this kind of analogy that, oh, you create this thing called a quantum state, this entangled state. Imagine exactly this Bell state is what we are talking about over here. So that's 2 qubits, right? So imagine an experiment was performed. Alice and Bob, or your 2 favorite names over here, got kind of one part of each of these qubits from this pair, and then they traveled off to wherever they're interested in. And now what's interesting about quantum entanglement is that if Alice were to measure her qubit in, on Mars or wherever, then her measurement result would tell her instantly about the state of Bob's qubit, wherever he might be, depending on how far spatially separated they might be. And while it seems interesting because people add in the word quantum in the beginning, what I'd like to emphasize is within that description that I gave, there is actually nothing interesting quantum happening, because you can take exactly this correlation vector and describe the experiment that we just did, where you replace, let's say, the quantum bits to envelopes containing, let's say, either always red paper or green paper. Contains 0 or 1 as well, but let's just make it completely really classical. So there's a joint preparation procedure, right? Just like we saw that there's a joint preparation procedure for these 2 qubits in order for them to end up in this entangled state, because you need to be able to physically perform the C0 operation on 2 of them. If they were not entangled before and you did not have access to prior entanglement in any way either. Then similarly, if you wanted to create perfect correlation, then in the lab, you created 2 envelopes where the joint preparation procedure for those 2 envelopes was that I will either put 2 red papers in both the envelopes or 2 green papers in both the envelopes. And Alice and Bob do not know which paper I've actually put in, just that this is the preparation procedure I've used. And then Alice and Bob are given their part of the envelopes, and both of them travel off, just like they did with the qubits. And now when Bob or Alice or any one of them opens up their envelope, no matter when they open up the envelopes, as soon as they see the color of the paper inside the envelope, instantly they know the color of the paper on the other side with Bob or Alice, or vice versa as well. Right? So exactly the same thing that has been mentioned in the popular science description of quantum entanglement is something that's completely reproducible via classical correlation as well. In fact, is just the description of perfect classical correlation. To make clear or make obvious the effects of quantum entanglement requires a bit more nuanced kind of description, right? Just like we had kind of a more nuanced evaluation of the quantum circuit that we just saw, to see interference effects. Similarly, to see the benefits of quantum entanglement and how quantum entanglement is different from classical correlations, we need slightly different experiments, maybe something like non-locality, or maybe an algorithm where the computation does something different, or operationally you're able to do an information processing task that's different from, or that's not achievable by a classical computation. And so that's what we'll do in kind of our session now, I think on Monday, where the 2 kind of pioneering quantum information experiments regarding this will be discussed: quantum teleportation and superdense coding. And for both of those, the kind of unit currency that we have, as is the case in nearly all quantum information processing tasks, is this entangled pair. So you assume that the parties performing the experiment are using as a resource prior access to this entangled state. And using this entangled state, now they can perform some information processing tasks that may not have been possible using only classical resources, and that then conveys the effect and benefits of quantum entanglement. All right, and I'll stop here for today then. Take questions, queries, concerns. I know the discussion on Discord has been about the rotation and reflection still. Book to study and that we're talking for. So I think the comprehensive book that usually is thrown around is Standard Nielsen and Chong for the theory. There are definitely more interesting popular science books as well. I'll share a few of them on Discord. And I think for the purpose of programming, I think the Jupyter notebooks that you have, IBM's own Qiskit tutorial course book as well, are excellent resources for getting started with the programming part of it. Open quantum systems are not going to be discussed within the bronze and silver workshops. as QWorld in general, we are working on preparing material for open quantum systems. Unfortunately, we won't see them in bronze and silver parts of the workshop. Between correlation and entanglement, when do we obtain correlation? So we'll have more to talk about correlation versus entanglement in our next lecture. For the moment, I think for what I want as a takeaway message is, if you follow the example that I gave with the envelopes, is to at least appreciate why perfect correlation is not the defining characteristic of entanglement, because perfect correlation is just a classical resource and classical description of property of a classical information, whereas entanglement is something slightly more nuanced. Why and how, we'll talk about it more. Within the example that I actually just gave, there is actually a distinction within that example, though, and we get now really subtle. Given, again, how you think about quantum interpretations, it's, the average understanding would be that when we prepare these two envelopes in our classical correlation, the values of the actual contents of the envelopes, right, whether it is containing a red paper or green paper, is fixed at the time of preparation, right? No one will think that, all right, somehow I will be able to magically change the envelope, the color of thingy in the envelope sometime later on after Alice and Bob have taken the envelopes away. It's fixed when I prepare the thingy. Whereas, as we will discuss later on as well, is what we understand for quantum information with the quantum entanglement version of the same experiment is the value is actually determined not at the time of preparation, but rather at the time of measurement. And while in terms of the statistics, it might not seem a big thing, but when you're talking about kind of information security and cryptography protocols, it is an interesting distinction, right? That somehow you're able to create a separation in the time when the commitment will be made regarding when the values are being fixed. And so that can play a crucial role in cryptographic protocols regarding bit commitment, let's say. Can you repeat to explain about C0 at preparing a Bell state? And the idea over here is if we assume that you have nothing else in the lab but just these two qubits prepared in state 00, then we need this. If you go back and look at the matrix representation of C0, C0 would be what you'd call a joint operation on the two qubits. You can't write it as something on qubit 1 tensor something on qubit 2, but it's rather a joint operation. And somehow it's because you perform this joint operation that ends up creating this entanglement where now the two qubits, the state vector representation has this property that you can't write it as qubit 1 tensor qubit 2. If the C0 wasn't there, then we aren't essentially preparing our Bell state. Right? But I'll stop babbling now, and because we're nearly out of time. Thank you, everyone. Thank you, Malu. I'll try to post these notes online via Discord and Canvas as well.
Excellent. Thank you very much for the interesting lecture, Jibran. Thank you also, Lindsay Bayak, for the flawless technical moderation behind the screens today. You have continuously been admitting people to have more than 350 participants again today. I would like to briefly look back with you and look ahead, because you have completed the 5th day of the Global Quantum Computing and Entrepreneurship Program today. Congratulations on that. That is a great achievement. You have learned about the basics of quantum mechanics, learned about the basics of quantum computing, and the basics of the quantum program. Yesterday, we had William Oliver here, professor of electrical engineering, computer science, and physics, and a Lincoln Laboratory Fellow and director of the Center for Quantum Engineering at MIT, who gave an introduction to quantum computing. Then QWorld's Jibran, introduction to quantum systems. And I highly encourage you to, next slide, to write summaries yourself and also look at summaries that others wrote. For example, these excellent summaries by Avril Mishra and Abba Naik, who wrote about yesterday that William Oliver discussed the timeline of classical and quantum computers, gates, advantages of quantum algorithms, benchmarking, then an introduction to superconducting qubits, layered architecture of quantum computers. And then Abba emphasizing QWorld's lecture, probability amplitudes, quantum operations, classical versus quantum coin flipping, and interpretations of quantum mechanics. Today, you learned some more about the entrepreneurial side, an entrepreneur's journey in this hot field of quantum and then reaching quantum silence. You will learn more about how that is reached, these millikelvin temperatures, next week in the lecture by Blue Force. And then today you continued with Jibran's basics of a quantum program and quantum operators on a qubit. Now that you know how roughly quantum computers work, we will have a very interesting session tomorrow where Shahar Kainan, CEO and founder of Polaris QB, will talk about an application, namely quantum computing for drug discovery. In her company, they scan billions of molecules in a huge chemical space to find molecules that are suitable for certain diseases. And this is really enabled by quantum computing to speed it up tens and tens of times. Then there will be a session by Anushka Srivastava from Qiskit Technologies about the control and readout of qubits, and a Q&A with three colleagues of hers at Qiskit. Saturday weekend will be fun time. We will have a session about quantum games with Ricardo Olanawa from Google, and then you can play quantum games yourselves. For example, quantum chess, quantum tic-tac-toe, and other games. If you think, oh, I don't have time for fun yet, I need to practice QBronze a bit more, there will be a mentoring session and Q&A offered by Jyoti from QWorld. So there you can ask all your questions and practice more. Next week, we will have many more interesting sessions. First of all, you will finish QBronze and you can earn your first certificate of this course, Quantum Programming 1. Then there will be a virtual lab tour at MIT where you can see the labs that William Oliver talked about. Also, you will learn about 3 types of quantum computers in more detail: superconducting qubits by IBM, neutral atoms, atom computing, and trapped ions, continuum. You will learn about the quantum internet, and there will be a career panel. There have been many questions about careers in science, and next week you will be able to hear more about that and ask your questions to experts. We look forward to seeing you tomorrow with quantum computing for drug discovery and Qiskit control and readout of qubits. Good luck with the quizzes today and the homework, and we will see each other on Discord to keep discussing. Thank you very much.